This is our first example working with Coulomb's law, where we are trying to find the net electric force on QA. Now I've already drawn the setup. Boom, as drawn on the left. I'm going to take a moment to note the trigonometry. We have a 3, 4, 5 triangle. We end up not actually needing the 5 centimeter side for this specific problem, but in the problems you're doing yourself, you will need to know that that is 5 centimeters right there. Okay, good. Identifying the system. Well, we're talking about QA. So that's this one, which is a positive charge. C is also a positive charge. B is a negative charge. I'm making those real evident right now because when I draw the forces, I need to know the positives and negatives. So QA, what's going on with QA? It's experiencing a force from B and it's experiencing a force from C. Let's do B first. B is negative, so the force of B on A is going to be attractive like that. One great thing about this is it's completely in the negative y direction, which is going to make a later step of trigonometry much easier. C is positive, A is positive, so it's going to be repulsive force on A. I'm going to draw it smaller because it's also farther away, and distance becomes really important when R squared is considered for Coulomb's law. Force of C on A. All right, forces have been drawn. Break results into components. It's not actually an issue on this one because they're already components in terms of X components and Y components, and there's C on A and there's B on A, and then there's going to be a total on A. That's our goal. C on A is completely to the left and not in Y. B on A is completely down and not in X at all. What is the magnitude of each of those forces? Well, C on A. C on A is going to be K, QA, QC over R squared, which is going to be 9E9 multiplied by QA has a 1 microcoulomb charge times 1E negative 6. C is a positive 3 microcoulombs times 3 E negative 6. And then the distance between them is 4 centimeters, 0.04 squared. Taking those, grabbing my calculator, and I got 9E9 times 1E negative 6 times 3E negative 6 divided by 0.04 squared gives me 16.875. This will be in newtons because we're dealing with a C on A's magnitude of the force. So I'm going to call that 16.9 newtons. newtons. B on A. Force of B on A in magnitude is going to be K QA QB over its radius distance away squared is going to be 99. QA is that same 1e negative 6. QB is going to be negative 2 microcoulombs, but I'm just doing magnitude, so I'm going to just say 2 microcoulombs, all divided by 3 centimeters away, squared. This is very similar to the previous one. Big difference is we're dealing with 2 instead of 3 microcoulombs, and it is 3 centimeters away, not 4, giving us a nice clean 20 newtons downwards. Okay, so I overdid it. Yes, the red one is longer, but not by as much as I exaggerated it. So I'm going to make this longer so they look similar in size, because they are similar in size, they're just not exactly the same. Which means our net force should be down and to the left. Electric on A will be negative 16.9 newtons left, and it will be 20 newtons down, which gives me 16.9 squared plus 20 squared, all square rooted. A magnitude of the electric force on A is going to be equal to 26.2 newtons. Break results in the components, that was easy. Add like components, that was actually a simple step. Double check results, yeah, it's a decent result. I can also give an angle of where this occurs, just as a one more thing. The angle that this occurs at is going to be this green angle right there. When I throw in my numbers into the calculator, it'll give me this angle due to a third quadrant issue, and then I will simply add 180 to it to get the correct number. So theta will be equal to 180 plus the inverse tangent of opposite over adjacent. Opposite is negative 20. Adjacent is going to be negative 16.9. Notice how those two negatives cancel? That's why it's going to give me a first quadrant answer, and why I'm adding the 180. So it'll be 180 plus inverse tangent of negative 20 divided by negative 16.9. Gives me a total result of 230 degrees. And that fits, looks like approximately 230 degrees. There you go. Results double checked. Example 1 done. Note when you're asked on your own to do problems for what's the net force on C and what's the net force on B, there will be components you have to break down, and the next two examples should show examples of that. Let's take a look at those next.